Okay, let's get this going. So if you've watched the video from last time, it seemed to be pretty quick. And even quicker than I expected. So, I think I set myself up to have a meeting today, right after class at 2:15, because I also want to see the faculty candidate talk at 3. So that means I have to finish on time or better yet early. Don't have terribly many notes, so we'll see what happens. Here's everywhere. And okay. So last time, that I covered for this problem, solving A equals B, where A is symmetric, positive, definite. So in this section 5.2, we're seeing 3 methods, and it's the second of the 3, all for this problem. So we're assuming A is symmetric, positive, definite throughout. So to recap, last time we had definite steepest descent. Where main step as this form, xk plus 1 is equal to xk plus alpha k rk, where rk is equal to b minus a xk, the residual, and alpha k is some chosen scaling parameter, scaling factor to make as much progress. Sorry, hold on for just one moment.
Yeah, 71, 72, 73, because those are the 4 classes you have to take. And then you have to take 771 and 772, that's math courses. Functional. Yeah, functional analysis, then numerical analysis, functional analysis after the week. And then Dr. Tiana does the numerical.
And you should have a transforming place in. Sure. Oh, thank you.
It was good. It's just mainly proof, doing proofs. Sit and then you listen to the lectures, but most of the lectures are just showing different things. And then your homework is entirely proof-based. Every single homework questions are proof, and you have to present the proofs. Normally there's like 2 or 3 people in the class, so you just alternate whoever presents.
How about like the support side?
There's like, yeah,
Yeah.
I mean, it's a basic PhD course, so there's resources online. You can just literally type in the question and get some help. But it's, of course, there's, I don't know, textbook. Well, there is a textbook. It's just like a reference.
Sorry about that. Wouldn't normally do that in the middle of class, but I expect to finish material anyway, and I feel like my house is falling apart, so I. um, um, yeah, not really, but yeah. So, okay. So this is Stephen's set. So, the direction that we take is called a search direction. And what was found with Steve's descent is this doesn't work so well. It's just technically progress is continually made toward a solution. The trouble is it's not very much progress. Yeah. Okay. So especially if the matrix is ill conditioned, can get really, really slow. And the problem is we have each residual RK is orthogonal to the previous residual. That's something that can be shown. But RK is not linearly dependent of prior residual. So RJ, J less than K minus 1. And this can be seen next, I think, I don't remember, but I demonstrated it. You know what? Oh, okay. Actually, that. I don't recall if I demonstrated it on the video. Did anyone watch the video?
I just went over the notes.
Okay,
I haven't seen this again.
okay.
It's not-
Anyway, I have MATLAB code that does a demonstration, and I believe I posted it.
Yeah,
It's the second one.
yeah, the
Okay.
code's posted.
Oh, good. Okay. Yeah. And what happens is it's 2x2 system. So there's only two linearly dependent directions you can possibly have. So if each direction is orthogonal to the previous one, then each direction is parallel to the one before that, and you get this zigzag pattern. So the goal now for improving on steepest descent is have a method in this form. Xk plus equal xk plus some scaling factor times some vector pk. So this is still the search direction, and pk is at least independent of all prior search directions. Now, I started to and I want to emphasize all, not just the previous one. Now, sorry, my mind's just like that today. So, you may notice in the notes that I started to write orthogonal. And it turns out it's actually not going to be possible to have each search direction orthogonal to all prior search directions. So we are settling for a lesser goal here. And we're not going to get there just yet. We don't actually arrive at a method of this form today, but on Thursday we will. And that's going to be the conjugate gradient method. So our intermediate goal that we can pull off is all the residuals each residual is orthogonal to all prior residuals. Now, so in this case, residuals are not the search directions. So in steepest descent are one and the same. In conjugate gradient, they will be different. In today's method, the Lanczos iteration, we're not really going to have search directions per se. But we will at least make residuals orthogonal, and that will be a step in the right direction. Okay. Right. So, So how are we going to do that? We're going to prescribe a form for the solution. Okay. And work with that to try to ensure orthogonal residuals. So we're going to prescribe each iterate xk will be equal to the initial guess x0. Now that is something you choose. If you want, you could just let it be a zero vector. Plus some matrix qk, which is going to be n by k, so n rows, k columns, and then times some vector yk. They'll take a linear combination of the columns of qk. Now, the only thing we're going to prescribe right now about qk is this: qk transpose qk is identity. Another way of putting that is all the columns form an orthonormal set. Okay. And I'm going to express capital QK as a column partition. The columns are these vectors, little q1, little q2, up to little qk. So all of these, all of those vectors, the little q's, are orthonormal. I want to emphasize this is not the same as saying that QK is an orthogonal matrix. It can't be, it's not square. So I do have a QK transpose QK as identity. QK transpose is not identity. But that is actually an orthogonal projection matrix. Okay, so right now I haven't said anything about what these are, except that they're orthonormal. So the idea is, how do we construct these so that they're orthonormal, and so that when I compute a residual from xk, that we ensure that each residual is orthogonal to all previous residuals. Okay. So first I'll specify how we can set the first column. I'm going to find the first residual R1 is B minus A X 0. Okay. If you were to look at prior notes, you might notice that I'm indexing a little differently. R1 is determined from X0. And I'm staying consistent with my book. But I can't remember why I did it this way instead of R0, it's B minus AX0. I'm sure I had some reason for doing that, and I actually plan to change it in another edition. But someone pointed out this is my indexing convention. So each residual, so RK plus 1 is determined from XK. All right. So then Q1 will be R1 normalized. Okay. All right, so then we have the first vector of our matrix. We need to see how to generate the other ones. Okay. So now you can see what formula I can get for each new residual after computing xk, how do we get rk plus 1? So the definition would be b minus a x k. But then I'm going to write xk using the form I have over there. So b minus a x0 plus 2k yk. And then I'll distribute the a through. And I'm going to have b minus ax0 minus aqk yk. But b minus ax0, that's just R1. Now, actually, I'm going to rewrite this definition of Q1 a little bit. I'm going to say Q1 is equal to R1 divided by beta naught, where beta naught is the norm of R1. Because I need that beta naught later. So I can rewrite this equation. I can say R1 is equal to beta naught Q1. But Q1 is the first column of a matrix capital QK. So I can write it as beta naught QK E1 minus A QK YK. So this gives us an idea of how the residual relates to the columns of capital QK. So if we look at the first residual, so R1 is a multiple of Q1. So R1 is in the span of Q1. Now, if I set k equal to 1 throughout this, then R2 is what's on the left side. So R2 would be a linear combination of this, which is just Q1, little q1. And then this, where we take A times Q1. Question so far? Now, if I go back and set k equal to 2, so now I'm looking at R3. So R3 involves, okay, Q1 again, but then we're taking whatever vectors make up capital Q and applying A to them. So I'd have Q1 itself, and then A times anything in here. So AQ1, but we already have that. And then A squared Q1. Okay. So in general, okay. RK belongs to the span of Q1. Okay. Actually, Q1 is a multiple of R1. So R1, AR1, A to A squared R1, all the way to A to the K minus 1, R1. And we label this fancy K of R1, A, then little k. And this is called a Krylov subspace. So a Krylov subspace involves an initial vector, a matrix, and a number indicating the dimension of the subspace. So you start with a vector, but you keep multiplying a vector by the matrix A. And you do it until you have this many vectors from a dimension of a subspace. And that's what a Krylov subspace is. So you can think of it as the set of all polynomials of A times your vector up to a certain degree. Okay.
So it's not A. Can you say that last part again?
Okay. So you can think of this as all their combinations of, or a set of all polynomials of A times the vector up to a certain degree, of the degree K minus 1. So what we'll do is we can let the columns of capital QK form an orthonormal basis for this Krylov subspace. Okay. Because since each residual it comes from the next Krylov subspace. So RK plus 1 would belong to the range of capital Q K plus 1. Yeah. The idea being that if the columns of capital QK already span a Krylov subspace, and all we're doing in this relationship is we're taking one of those columns and we're multiplying all the columns by A, that just gives us the next Krylov subspace. So now I want to use this knowledge to ensure that RK plus 1 is orthogonal to all previous residuals. So, okay, actually, this I'm going to want to keep. So make RK plus 1 orthogonal to all previous residuals, R1, R2, up to RK. What we need is capital QK transpose RK plus 1 is 0. Because these prior residuals belong to the range of this matrix. Now I have an expression for RK plus 1. It's right here. So QK transpose, so RK plus 1 is this, so beta naught QK E1 minus A QK YK. Now, QK transpose QK is identity. So I just get beta naught E1 minus capital TK YK, where capital TK is defined to be QK transpose A QK. And this must be 0. Once we have capital QK, we know how to get YK. We just solve a system. TK YK equals beta naught E1. And this is a K by K matrix. So each iteration, to get our new X, we're solving a K by K system. Now, of course, that means that system's going to grow with the iterations. And right now, we don't know anything about TK, but we're going to find out. So what do we know about TK? First of all, TK is metric positive definite. I can show that real quick. I have a vector X transpose TK X. But TK is defined to be QK transpose AQK. So I can write this as the vector QKX transpose A times the vector QKX. And QK has orthonormal columns. So QK is non-singular. So if X is non-zero, that means that QKX is, non-zero. Then QKX is non-zero. So the fact that A is assumed to be SPD tells us that this is SPD because this is now known to be positive. All right, so we know that TK is at least symmetric positive definite. So it's like we're creating our original symmetric positive definite system for that's n by n for a K by K one each iteration. Okay. But we need to know more about TK than that, because what if TK is a full matrix? That the system keeps growing in size of each iteration. So that wouldn't be so good. But as I'm going to show you, TK is most definitely not a full or dense matrix. All right. So, as the columns of QK come from a Krylov subspace, we have the following. Each vector QK is a polynomial of degree k minus 1 of A times R1. And these polynomials, P0, P1, Pk minus 1 are called orthogonal polynomials. Now, orthogonal in what sense, though? This inner product. So the inner product would be of two functions f and g is R1 transpose f of A, g of A, R1. Okay. What we have is the inner product of Pi and Pj would be R1 transpose, Pi of A, Pj of A, R1. But that's going to be Qi plus 1 transpose Qj plus 1. And because the little q's are orthonormal, that is equal to 0 if I not equal to j and 1 if they are equal. Now, one thing that's known about orthogonal polynomials, I've actually proved elsewhere in my book. I mentioned the section and notes, but I'll just give that full factoid here. Orthogonal polynomials satisfy what's called a three-term recurrence relation. And that three-term recurrence, in other words, each polynomial depends on the previous two. So I have coefficients beta j, pj, a equal to, whoops, no, not of a, of lambda. lambda minus alpha j, j minus 1 of lambda minus beta j minus 1, pj minus 2 of lambda. All right, so that's the relationship with the polynomial satisfied. And this holds for j starting from 1. Now, when you have a 3-term recurrence relation, with each many previous 2, that means you need 2 initial conditions. And those initial conditions are P0 of lambda is 1 over beta 0, because the first column Q1, you take the first residual R1 and you just divide it by beta 0. So that's the constant polynomial in this. And then you also have P sub minus 1 of lambda, that's a 0. So that describes all of your orthogonal polynomials. So now what I can do is I can take this recurrence relation and substitute the matrix A in for lambda. So then I have a matrix equation. And then I multiply both sides of that matrix equation on the right by R1. So I have beta j, pj of A, R1 is equal to A minus alpha j identity, pj minus 1 of A, R1, minus beta j minus 1, pj minus 2 of A times R1. But then I use this relationship right here to write everything in terms of the Q's. Now I have beta j q j plus 1 is equal to a qj minus alpha j j minus beta j minus 1 qj minus 1. Or if I just rearrange it, aqj is equal to beta j minus 1 qj minus 1 plus alpha j qj plus beta j q j plus 1. Okay. Now, if I write out this recurrence for j equal to 1, 2, 3, and so forth, and if a whole mess is in the notes, okay. So, okay, so we apply this. Big 1, 2, up to k. Then I would have a capital QK is equal to this matrix that has the alphas on a diagonal, and then it has the betas above and below, symmetric matrix. Times QK, because here we have all these coefficients times the columns of capital QK. And in each row, like in each case, we're multiplying 3 coefficients times 3 columns of capital QK. Now, when J is equal to K, there's going to be this term. All right, beta K little q K plus 1. So that is not included in this. But this only pops up in the last column of this matrix equation. So I multiply it by EK transpose. So this right here is a matrix so this right here is a matrix. It's not a product. It's a matrix that's entirely 0, except in the last column it has this part that I've highlighted. Wait a minute. Sorry, I goofed. QK is in the wrong spot. Hold on. It doesn't belong here. It actually belongs to the left of the matrix. And AQK is equal back. Whoops. Right. But the thing is, now, suppose I multiply both sides on the left by QK transpose. So then on the left, I'd have QK transpose AQK, which was previously identified to be TK. If I had QK transpose QK's identity, so that goes away. QK is orthogonal to this, so that's 0. So this matrix must be TK. So we already know symmetric positive definites, but now we also know that it is tridiagonal. So solving this system involving TK to get YK is easy. We already seen when we talked about banded matrices way back in chapter 3 that you can solve an K by K system in order K operations. All right.
Would this be one of the cases similar to earlier to where we wouldn't actually need to ever construct T if we're using this, like if we're coding it?
Oh. Oh, like construct T?
Yeah.
Let's see. Well, you would need to generate these.
Yeah.
Okay.
We're using it to solve, would we just
Okay.
for the 2 vectors, the alpha and beta vectors?
Yeah. Well, okay. We will get to something like that when we get to conjugate gradient, which is going to be built from this. But it takes a lot of work to make it happen. You actually have to like factorize TK and work with factorization to avoid constructing it at all. So, and once I write out the algorithms coming from this, I'll be able to explain more about what the issues are. Okay. Now, as far as the residual, so RK plus 1 which was, that's B minus AXK. So that was, okay. Right. So that was established earlier to be equal to beta naught QKE1 minus A QKYK. But now that I know what AQK is, AQK is equal to QKTK plus beta K, little QK plus 1, EK transpose, all times YK. But now this is equal to beta naught QKE1. Actually, no. Let's factor out QK from the first two terms. Beta naught E1 minus EK YK minus beta K QK plus 1 EK transpose YK. Well, this is 0 because YK is chosen to make it 0. And this right here in parentheses, that's a scalar. It's just the last element of a vector YK. So the residual is proportional to the next orthonormal vector. So that's what ensures that each residual is orthogonal to all previous residuals. Sorry, need some water real quick. Okay. So, so we need an efficient way to get the alphas and betas, and also each new vector, like little QK from previous ones. So, so we have a relatively simple relationship that gives us each new Q from our previous ones. Okay. It is just recurrence relation. We just need the alphas and betas. So what I'm going to do is take the inner product, the dot product of both sides with QJ. Now I have beta J, QJ transpose, QJ plus 1 equals QJ transpose AQJ minus alpha J, QJ transpose QJ minus beta J minus 1, QJ transpose QJ minus 1. But the Q's are orthonormal. So that's 0. This is 1. And that's 0. So that means that alpha j is equal to qj transpose AQJ. That worked out easily enough. And then as for the betas, well, if I define a vector Vj to be equal to the right side of this, the assumption is, suppose I've already computed everything up to Qj, and I also have alpha j, and I have previous betas. Okay. So then I have this relationship, beta j, Qj plus 1 is equal to Vj. But Qj plus 1 is a unit vector. So beta j just has to be the magnitude. So beta j is just the 2 norm of Vj. And there, so then the next Q is Vj over beta j. Make it more of a fraction. Okay. Now I can write out the whole algorithm. Well, the Lanczos algorithm solving x equals b in a symmetric positive definite case and generating orthogonal residuals. So, so first you choose your initial guess, x0. And then I'll set my iteration count, k equal to 0. I'm going to set this vector v0 to be my first residual. And then I'll set this vector q0, because I mean, q0 is not really going to be part of any matrix. It's for convenience of setting it to the 0 value. So then I'll have a loop that will keep going as long as I have not converged. Okay. So first, I'll take my v vector and take its 2 norm to get my beta. And then I'll get my q vector is ek over beta k. And then I'm going to bump up my iteration count here, k equals k plus 1. So this vector will henceforth be known as qk, not qk plus 1. Now I'm going to form this one matrix vector multiplication that will be needed later. And then alpha k is qk transpose vk, which is consistent with this formula that I wrote earlier for alpha. I'm just computing this. I'm just computing this part up front. And I've also computed by the matrix vector product the first part of this vector. So now I'm just going to subtract off the rest of the terms. So now, okay. So BK is equal to itself minus alpha K QK minus beta K minus 1 QK minus 1. Now, this generates all the Q's and the alphas and betas, but it's still a matter of actually solving a system. So you would have xk equals x naught plus capital QK TK inverse you know, you want. Now, you're not actually going to form the inverse, and you're going to solve it by, Gauss elimination or whatever. This is your vector yk. Right.
So, for the while converge, while not converge, essentially you're just checking to see if
If xk is converging.
the BK just changes by less than some tolerance.
Or xk.
Okay.
Yeah, exactly. That's what we're solving for. Yeah, because the BKs, they're going to be orthogonal. Yeah. Now. Okay. Now this is an improvement on steepest descent, just because the residuals are orthogonal. The problem is, we need to store QK and TK, because this is not the typical form for a non-stationary method. Even steepest descent was written as in the form of a general non-stationary method where each new iterant was equal to the previous iterant plus some multiple search direction. This is not. Here we have the new iterant is equal to the initial guess plus this matrix vector product. The problem is when I compute these vectors yk, they don't build on each other. Like if I compare yk to yk minus 1, what I'd really like is for the first k minus 1 elements of yk to be yk minus 1. Because then I wouldn't be computing it all over again. I would just be computing the next element. That would give me a way to have each iterant built on the previous iterant. I can't do that the way this algorithm is laid out. So this is not in classical non-stationary form, where we have xk plus 1 is equal to xk plus alpha k pk, where pk is some search direction. So although we have improved on steepest descent, we still have work to do. Yeah, I guess let's go back to your question earlier about having to, form TK. Unfortunately, because these vectors are all different, we do need to form it. So I will do a lot of work on Thursday to get out of having to form it. And it'll be well worth it because then we will have a method of this form. The key ingredient is going to be taking this tridiagonal matrix as TK and factorizing it. And that will lead to the relationships we need. So kind of cool. It's labor intensive. So, okay. So. Oh, I've been doing it on time. Oh, actually doing pretty well on time. Yeah, okay, cool. Questions about any of this? Or homework? Okay, okay. All right. Okay. Things I remember in years past, I would spend like a few whole class periods going through conjugate derivation of conjugate radiate, which is the next method coming up. And somehow I have it squeezed into one class. Not sure how I'm going to do that. Maybe I'm going to gloss over a lot of things. I don't know. I haven't looked at my notes, but it's gonna be fun. Okay. All right, then let's blow this pop stand.